Contexts are very important when it comes to large language models. Context refers to the preceding text or conversation history that the model uses to generate relevant and coherent responses. There are two types of context. One is short context and the other one is long context. Short context refers to a limited amount of information, usually the most recent or current input given to the model. In a conversation, this might be the last few sentences or the current question being asked. Context allows the model to respond directly to the immediate queries but might limit its ability to understand deeper or more nuanced aspects of a conversation that depends on earlier information. Long context, on the other hand, involves more extensive range of information, potentially involving the entire conversation history or a large body of text. Long context is crucial for understanding complex inquiries, maintaining coherence over a long conversation, and recognizing references to earlier statements or questions. It enables the model to generate responses that are more relevant and informed by the broader conversation or topic. Now, the reason why I'm discussing this short and long context is in the wake of this new paper which is proposing activation beacon. This is actually quite a groundbreaking paper if you really think about it, because if whatever they are saying is true in this paper, then it means then we are on the cusp of unlimited context. Now, I discussed one another model called as Mamba, which is a state space model earlier, and that is the it involves RWKV, which is RNN, and they both have state to remember earlier context. But this paper suggests that encoding a state and dumping it at the beginning of transformer context sliding window like an efficient summary of earlier context, thus effectively making transformer stateful for pre-context information, which could mean that infinite but lossy context memory. Or in another simple word, what is happening is that this proposal, which is quite neat, I would say, it depends on activation compression to work. So if you go into the detail of this paper, and there are a lot of things here, then what they are saying is that they process a sequence of n tokens using a sliding window tuned to the max context size of the base model. First, they sample a condensation factor, which is alpha, which determines number of beacons to condense a window, for example 4096 token, down into say 4 beacons. And then they adapt this so that the longer the context, the higher the number of beacons used, because you need to store more activations, as you can see here. Now, then they pre-fill the window with 1-k real tokens from the prompt, and then they generate k beacons, each of which records some information about the activations of some of the previous tokens. They call this h underscore b for each beacon b in the paper. There are a few things which are still unclear to me, and I'll be honest. For example, I'm unclear if this is trained behavior during the fine tuning or it is statically processed from existing activation. But just suppose if this is if h underscore b is gradable, then I think there is no reason why it can't be trained from the forward equation. Anyway, next step, they slide the window up to where the beacon began, and then the pre-fill the next chunk prompt to fill out the window. Lastly, they sample a new condensation factor, which is alpha and k, and slide the window up so there is room for k more beacons to generate. And it keeps looping this until it starts to do this auto-regressively. And they also have described it in this diagram where you can see that activation beacon and the attention scheme of beacon is working with auto-regression as I just described. If you look at these equations and if you read through this paper, what I have understood is that what is happening here is that basically the beacons store the condensed activation from the previous window of token, which also accumulates activation from the previous beacons, which condenses activation from the previous window, and so on and so forth. So this way, they can effectively retain the long context by forwarding their activations through successive windows beacon without needing to evaluate more than one context. So another thing which I'm quite intrigued about is that beacon always gets the attention sync treatment. So this effectively reboosts activations from long ago each round. But I think there is also some information loss due to the compression. So it is like some sort of human like blurry memory with a strong attention score. Now I think where this very long context is working, because this uses a sliding window where the first few tokens, or many depending on how long the sequence is already, just encode the activation state at 3 layers from the previous window, as I showed you in above diagram. Sorry, let me quickly go up and show you, it will be more clearer. This one. So because these sliding windows are within the max context length, it doesn't trigger the extrapolation problem. So that is one another advantage. Anyway, I will also drop the link to this paper in video's description so that you can read along further. And I hope that you enjoyed this, because this is going to be a really massive thing if it is true, because you get fixed memory consumption, inference time can grow linearly, and you can train this to use with short window, but then it works on long window generation too, and there are a lot of other things. That's it. I hope that you liked it. If you did, please consider subscribing to the channel, and if you're already subscribed, please share it among your network, as it helps. Thank you very much.